and welcome back to this problem solving session for the NPTEL course Foundation Engineering. So currently we are in week 7, and the last week we started learning a new topic called file foundation. So in the last class we basically solved a few problems regarding the determination of load carrying capacity, uh, essentially the safe load carrying capacity of a file which is basically constructed in a granular soil deposit. So we we have seen the use of static pilot formula, uh, and under this heading static pilot formula, the application of Tomlinson's method, specifically the application of Tomlinson's method for the calculation of pile load carrying capacity in purely granular soil deposit, and obviously under completion. Okay, so in the present week we moved further. So we learned a few additional topics regarding this same aspect, that is pile capacity. So in this week we learned how to determine the load carrying capacity of pile in cohesive soil. So in addition, in the last week we have seen the theories which are developed to calculate the load carrying capacity in granular soil. So in this week, in addition to granular soil, we also learned how to determine the load carrying capacity of a pile in cohesive soil. So apart from that, we have also learned the load carrying capacity of underdamped pile in clay with single bulb or multiple number of bulbs. Okay, so we'll see what is meant by this underdamped pile. Though I think we had discussed about this topic in the earlier session. Now, to determine the load carrying capacity of this conventional pile, that is a shaft of uniform diameter, or this pile called underdamped having single or multiple number of bulbs, different theories are basically evolved in the literature. So the very first method which we started learning, that is called static pile load formula. So with this formula we can easily determine the capacity, load carrying capacity of a pile in any soil, that is granular or cohesive, obviously under compression. So these theories basically divided into these categories, means static pile load formula, Tomlinson's method, Mehrab solutions, and then IS code recommendations. Okay, so all these methods are categorized and or basically put under the heading of static pile load formula. Now, in addition to the static pile load formula, the capacity of a pile can be determined using pile load test. And as you know, this is an in situ test. So you can directly calculate the capacity of a pile at the field condition. Now this pile load test is of three types. So vertical, lateral, and pull out. So for your kind information, for the specific course, our concern will be mostly on the vertical pile load test. Okay, so this vertical pile load test is usually used to determine the load settlement behavior and consequently the allowable load on a single pile or a group pile. Okay, group of piles. Okay. Now this lateral and pull out test, this is used when you have to consider or you have to calculate the lateral or uplift resistance of the pile. So vertical pile load test is essentially useful when the pile is basically subjected to a load which is compressive in nature, and in the case of lateral or pull out, vertical, it's compressive, and as well as it is applied in the vertical direction, axial direction of the pile. And in case of lateral or pull out, the load specifically for lateral, it's basically acted in the horizontal direction, and for pull out, it's again in the axial, but it's tensile in nature. That is, it is basically you are determining the uplift resistance of a pile. So this type of pilot test, when you will be basically performing this kind of pilot test, so you should know different terminologies like initial test, routine test, test pile, working pile, continuous loading, and cyclic loading. So I hope all of you have gone through the lecture content. So from that you can easily get an idea about this terminology. So what is called or what is meant by this initial test or routine test or test pile, working pile, continuous loading, cyclic loading. Okay. So just for a brief explanation, this initial test usually performed on test pile, and this test pile is not coming under the pile which is basically under the superstructure. That means test pile doesn't bear the load which is coming from the superstructure. It's basically constructed only for the testing purpose. Whereas this working pile, this is a pile which comes under the superstructure, which comes under the substructure of a given superstructure, and obviously it will carry some load which is basically coming from the superstructure, and the test which is basically performed on this kind of working pile, this is known as routine test. Further, in the case of continuous loading, the load is basically monotonically increased to certain level, and that is already decided, or you know what is that limit of load up to which the test should be performed. Okay, so considering that aspect, this load is basically increased from some initial value or zero value to some certain extent. So this kind of loading is known as continuous loading. In contrast, cyclic loading, the loading first basically increased to some level, then it's released to zero, then again the load is basically increased some further subsequent higher level, and then released to zero. So in this manner, when the pile is basically tested, the nature of loading is called cyclic loading. Okay, so the load settlement behavior. So if I draw the load settlement behavior of a pile under these two kinds of loading, so first of all, continuous loading. So this is the load, and this is the corresponding settlement of the pile. Okay, so you will basically observe this kind of plot for continuous loading. So as if the load is basically increased in a monotonic fashion. Whereas in the second scenario, that is for cyclic loading, your load is first increased to some level, then it's released. Okay, it's released, then again it's basically increased to some higher level as compared to the previous one, then it's released, and it's basically proceeding in this fashion. Okay, so as you can see, when you release the load, the curve doesn't go back the initial starting position. Why? Because some plastic supplement will take place, and that's why this curve will not meet exactly the initial starting position. Okay, so this is the very fundamental. When this load is applied, you will be having settlement, and the settlement will be having two components, so the elastic component and the plastic component. So due to plastic component or plastic supplement, will never expect that the curve will meet exactly, or curve will go back exactly at the initial starting position. Okay, now this IS code, IS 2911 part 4 1979. So for a detailed procedure that how to perform pilot test, you can go through this standard. And again, after performing the pilot test, you will be having the load settlement behavior or load settlement data. So from that data, if you plot the curve, so you can easily determine the allowable load on single pile and group of piles. And this determination of allowable load for a single pile or group of piles, recommendations are basically prescribed in this procedure IS 2911 part 4, part 1. Okay, so that we'll see through a numerical problem, example problem in this session. And most importantly, from the cyclic load test data, so you can determine the tip resistance and the frictional resistance separately. So as you know that when a pile is basically subjected to some load, so suppose this is the pile of length L and diameter D, and it's subjected to some load Q. So this load is basically partly supported by the mobilized friction along the length of the pile, and the rest of the load is basically supported by this point bearing, okay, bearing resistance at the pile tip. Now from the continuous loading or low pile load test, which is basically which only consider this continuous loading, you cannot get the resistance, tip resistance and the frictional resistance separately. Whereas in case of cyclic load test data, so if you have the cyclic load test data, so you can determine the tip resistance and the frictional resistance of the pile separately, though this procedure is quite laborious. However, you can determine this resistance separately by utilizing the cyclic load test data. And I hope so our sir basically explain this part very clearly. Okay, so if you go through the lecture content, so you can again get an idea about this aspect, that is determination of tip resistance and frictional resistance from cyclic pile load test data. Okay, so now we'll start our today's session with this problem. So a concrete pile of diameter 400 mm and length 15 meter rests in a uniform deposit of dense saturated sand. Calculate the safe load carrying capacity of the pile in kilonewton if the water table is at the ground level. So these are the properties given to this problem for determining the safe load carrying capacity of the given pile. So the properties are friction angle, that is 40 degree, earth pressure coefficient, that is 2, saturated unit weight of the dense sand 15 kilonewton per meter cube, and 2 bearing capacity factors N gamma and NQ. So one additional statement is basically mentioned in this problem, that you have to consider the critical length concept and the appropriate value of critical length. Further, you have to use the delta value according to the recommendations given by IS 2911 part 1 2010. Okay, so it's very clear that you have to use the static pile load formula. Again, under the static pile load formula, in the previous session we have basically applied that Tomlinson's method to determine the safe load carrying capacity. But in this problem, we'll see the application of IS code recommendations to determine the safe load carrying capacity of a given pile. Okay, so therefore we'll first see the recommendations given by this Indian standard IS 2911 part 1 section 2 2010. Okay, so this is a snapshot which is taken from this standard, and as you can see, for piles in granular soils, annexure B will give you the load carrying capacity of piles, obviously for static or by static analysis. So this is the expression. So QU equals to AP half D gamma N gamma plus PD NQ plus summation I equals to 1 to N KI PDI tan delta I ASI. So it's very similar to the formula which is given by Tomlinson's method. So the only exception is that this component we are considering additionally. Okay, so this is the additional component, half d gamma n gamma. Okay, so this is the additional component. Now this part, the first part will give you, so this corresponds to the tip resistance. Okay, so pile tip resistance. And the second component, this corresponds to skin resistance. And as a whole, the total contribution coming from the tip resistance and skin resistance will give you the ultimate resistance. Now if you divide this ultimate resistance by the recommended or prescribed factor of safety, you will be having the safe load carrying capacity of the given pile. Now we'll have a quick look for each of these individual parameters which are involved in this equation. So first of all, AP, this is the cross-sectional area at the pile tip. Then D, this is the diameter of the pile. Gamma, this is the unit weight of the soil. N gamma, this is bearing capacity factor contributed by the unit weight of the soil. PD, this is the effective overburden, vertical overburden pressure at the pile tip level. NQ, this is bearing capacity factor but contributed by the surcharge in the sense this PD component. And in the second part, Ki, this is the earth pressure coefficient for ith layer. PDI, this is the average effective overburden pressure, vertical overburden pressure for that ith layer. Tan delta I, this is the this delta I, this is the friction between the what I can say, so this is the angle of wall friction between the pile and soil for the ith layer. And ASI, this is the surface area of the pile shaft in the ith layer. Okay, now why this ith layer is basically considered here? So this is considered only because of the variation in the the skin friction resistance starting from the pile top to the pile tip. So as you go below from the pile top to the pile tip, so you will be having a variation in the skin friction resistance. So you have to take care of the skin friction resistance in a layer wise fashion. If the soil which you are basically encountering in the field is basically a layered soil, or you are you basically encounter some water table inside the soil or inside the pile lane, so in that case you have to basically go for this layer wise fashion. Okay, so that we have seen in the last class. Okay, so first of all we'll try to summarize the given data which are given to this problem. So D, okay, so this is capital D. So this is capital D. So this is 0.4 meter. Then gamma, that will use basically gamma submerged because the entire soil mass is under submerged condition. Okay, so this is the groundwater table which is basically located at the ground surface. So gamma submerged, that will be gamma sat minus gamma W, so 15 minus 10, that is 5 kilonewton per meter cube. So this unit weight we will be using for the calculation of load carrying capacity of the given pile. Okay, then N gamma given as 109.41 and NQ, so this is 130, and this AP, obviously this will be pi by 4 d square, and AS, so this will take it as okay, this is pi dl simply. Okay, so we'll basically consider this L separately when we'll be calculating the load carrying capacity of the pile. Now one more thing that we have to keep in mind, that is we have to consider the critical length concept, and accordingly we have to adopt the length of the value of critical length. Okay, so before that we'll basically note down the value for this angle of wall friction between the soil and the pile material. Now for this value we have to go for the recommendations given in this Indian standard. So as you can see, this delta angle of wall friction, so this delta value, I hope this is, you can take it from this notes. Okay, so this is so the delta, the angle of wall friction may be taken equal to the friction angle of the soil around the pile stem. So this is basically described in note 4. So the delta value, if you go for IS recommendations, then delta value you can take it as the friction angle of the soil around the pile stem, that is 40 degree for the given problem. Okay, now what is critical length? So critical length, so if this is the whole length of the pile, and if this pile is basically subjected to some point load, some load at its top, so as you can see that first the skin friction will be mobilized, and after that the load is basically increased, then the remaining load will be taken over or supported by the point bearing resistance, that is resistance given by the pile tip. Okay, now if you see the skin friction resistance, as I mentioned earlier, so it will basically increase from the pile top to the pile tip if you don't consider the critical length concept. So it will basically increase as per usual fashion, means depending on the effective vertical overburden pressure. However, if you consider the critical length concept, this mobilization of the skin friction resistance will be limited up to a certain length of the pile. Suppose this is the certain length of the pile, and this is known as L critical. So this mobilization will be resisted up to a certain length of the pile. Now over the remaining length of the pile, that is L minus LCR, here the skin friction will remain constant. So whatever the mobilized skin friction at the level of L critical, so that will remain same over the remaining length of the pile. So this is the critical length concept. So we have to use this critical length concept for this problem. Now before utilizing this concept, we should know what is the critical length of the given pile. Now again, to determine the or evaluate the critical length of the given pile, we have to consider this note 5. So in working out pile capacity by static formula, the maximum effective overburden at the pile tip should correspond to the critical depth, which may be taken as 15 times of the diameter of the pile shaft for phi less than equals to 30 degree, and increasing to 20 times for phi greater than or equals to 40 degree. So something like this, that this L critical, so this would be 15 times of the pile diameter when phi is less than or equal to 30 degree, and it will be increasing to or increased to 20 times of the pile diameter if phi value is greater than or equal to 40 degree. And you have to in between these two phi values, 30 degree and 40 degree, you have to go for a linear integration. Now since the phi value for the given soil is given as 40 degree, so the LCR, the critical length or critical depth, will be 20 times of the D. So this value will be appropriate for the given soil condition. That means it will be 20 multiplied by 0.4, that means 8 meter. Okay. So in this way we can calculate the critical length of the given pile. Now we'll start solving this problem by calculating the individual component, that is the pile tip resistance, ultimate pile tip resistance, and the ultimate skin friction resistance. Now for calculating the tip resistance, so this first component, so QPU, so this is, you can denote as QPU, and this is QS, okay, or QS. So QPU, this is half AP times half D gamma N gamma. Obviously this will be D gamma sap for the given problem, plus PD NQ. Now what is PD? So for calculating PD, you should know what is the effective vertical overburden pressure at the pile tip. Okay, so suppose this is the elevation, so this is 0 meter, and this is minus 20 meter, and somewhat here, so this is minus 8 meter. Okay, so this is the length of the pile is not 20, the length of the pile is basically 15. So this is 15, so this will be somewhere here, minus 8 meter. Now the effective overburden pressure, it will basically follow a linear variation, since you are having some uniform deposit, and again the water table is basically located at the ground surface. Now as per the critical length concept, this will not be the scenario, because as per the critical length concept, the effective overburden pressure will increase linearly only up to the level of critical length, and then for the remaining length of the pile, this value, whatever value you have at the level of critical length, that value will remain constant for the remaining length of the pile, means this 7 meter of this length. So for the initial 8 meter of the pile length, you will be having a linear variation in the effective overburden pressure. After that, the effective overburden pressure will become constant. Now what is this value? So this value would be 5 times 8. This 5 is the submerged unit weight of the soil, that is rain sand, and this is the height, this is the depth, so that is 40 kPa. Okay, and this value will remain constant up to the pile tip, from this critical length to the pile tip. So this is again 40 kPa. Okay, so therefore this, for the calculation of QPU, so first of all AP, this will be pi by 4 d square, so pi by 4 multiplied by 0.4 square, since the diameter of the pile is given as 0.4 meter, then half multiplied by 0.4, gamma sub is 5, n gamma is, I hope, 109.41, plus PD, just now we have calculated, so this is the PD value. Okay, so this is PD, so PD, this is 40, and NQ, this is given as 130. So if you calculate, so this value will be 667.2 kilonewton. Okay, so this is 667.2 kilonewton. Now this is for the ultimate point bearing resistance. Now Coming to the second part, that is the ultimate skin resistance QS. You have to consider two segments. You have to consider basically two layers. Okay, so this is I equals to 1 and this is I equals to 2, because corresponding to these two layers the variation is different. Variation in the effective overburden pressure is different. So depending on the variation, you have to basically divide the given soil mass into some layers. Okay, now for this current problem we have to divide this given soil mass into two layers, because each of this layer, in the first layer the effective overburden is varying from 0 to 40 kPa in a linear fashion, and for the second layer it is constant, it's not varying. So this QS, so first of all this will be K multiplied by, so this is Ki multiplied by PDI multiplied by tan delta I multiplied by ASI. So K, this is 2 for both the layers. Then PDI. Now what is PDI? PDI is the effective average of the effective overburden pressure corresponding to ith layer. Now for I equals to 1, the average of the effective overburden pressure is 0 plus 40 by 2. 0 at the top and 40 at the bottom of this layer. So 0 plus 40 divided by 2. Then tan delta I. So delta, we have calculated this value as 5 for the given problem. So 40 degree into ASI. Now coming to ASI, this is the formula pi dl. So it will be pi then multiplied by 0. Now what is L? L for this layer is basically 8 minus 0. Okay, so this is for layer 1. So similarly for layer 2, this will be 2 multiplied by here the average of the effective overburden pressure is simply 40, then tan 40 multiplied by pi into 0.2 into 15 minus 8. Okay, so this is the contribution to the skin friction resistance from layer 2. Okay, now if you calculate, so the first component I think it will become 337.42 and the second component will become 590.49. So please cross check these values. Okay, so I may be wrong for the calculation. So this will be ultimately 337.42 plus 590.49, so 927.91 kilometer. So therefore the ultimate resistance of the pile, so this will be 667.2 plus 927.91. That means 1595.1 kilometer. But we have to calculate the safe load carrying capacity, that is we have to divide the ultimate load by some factor of safety. Now this factor of safety, what would be the value for factor of safety? What is the recommended value of factor of safety to calculate the safe load carrying capacity? So this is nothing but 2.5. Okay, so you can take the recommended factor of safety or the desired factor of safety as 2.5. So this value would be 638 kilometers. This is the answer. Okay, so in this way you can calculate the safe load carrying capacity of the given pile. Yeah. Do you have any confusion?
Sir,
Huh.
wait 2 minutes. Let me complete of this.
Hello.
Hello.
Huh. Tell me.
Let me complete up to this survey 2 minutes.
Okay, I'm not getting you. So you are facing any network issues or what you are trying to say?
I'm saying that wait 2 minutes, sir.
Okay, okay, okay.
Please open first PPT, sir. First question.
This one.
Yes, sir. Yes, sir. Let it be completed first, sir. Wait 2 minutes.
Okay. Okay, so please let me know if you are done with this problem. Okay.
Sir,
Huh.
एक बार check करो, sir.
This slide.
Oh, no, sir.
This one.
Yes, sir. Yes, sir.
Okay.
Yes. Completed, sir.
Okay.
Next.
Thank you.
No, no, sir. Second page, sir. Yes, sir. What page, sir? Next. Okay, sir. Further, you can proceed now, sir.
Okay. Thank you. Okay. So now we'll take this problem, problem 2. So where a 15-meter long concrete pile with a diameter of 0.3 meter rests in a layered soil deposit consisting of dry sand with properties as shown in the table below. Now, the water table is at a great depth. If the safe load carrying capacity of the pile was calculated to be 1380 kilonewton using Tomlinson's method, find out the skin frictional resistance of the pile in layer 3. So these are the few given data. So first of all, the bearing capacity factor 130. The angle of friction between the pile and the soil is wall friction between the pile and soil is 0.75 times pi, and here we need not to consider the critical length concept. Okay, so the first and the major difference between the previous and this present problem is that in the earlier problem the dense sand layer was basically homogeneous, so we basically consider only a single layer uh, uh, for the for determining the pile load capacity. Now in this problem it's basically a layer deposit, and you are basically constructing the pile in this layer deposit with these dimensions, that is length is 15 meter and the diameter is 0.3 meter. Now the second difference is that, so earlier in the problem, so you have basically calculated the safe load carrying capacity by considering tip resistance and skin friction resistance. Now in this problem, the safe load carrying capacity is given to you. Now what you have to do, you have to basically figure out the skin frictional resistance contributed only by the layer 3. Okay, now we'll check or we'll take a look for the properties which are given to this problem, soil properties. So 0 to 6 meter, this is one layer, the unit weight is 15 kilonewton per meter cube, and the angle of internal friction is 30 degree, and the earth pressure coefficient is 1. Now for the second layer, which is basically extended from 6 meter to 10 meter, that is with a thickness of 4 meter, the unit weight is 18 kilonewton per meter cube, angle of internal friction is 35 degree, and the earth pressure coefficient is 1.5. Now for the third layer, which is having a thickness of 5 meter, the unit weight is 20 kilonewton per meter cube, angle of internal friction and the earth pressure coefficient are not given to this problem. So that's why we have to calculate the safe load carrying, the frictional resistance contributed by this layer using the safe load carrying capacity of the pile. Okay, so it's very very easy and straightforward problem because you know that this safe load carrying capacity, this is nothing but the ultimate load carrying capacity divided by the factor of safety. Okay, now from this you can easily get the ultimate load carrying capacity as 1380. So this is the safe load carrying capacity mentioned in this problem and multiplied by the factor of safety. So this is 2.5. Now if you multiply 1380 with 2.5, so it will be 3450 kilonewton as the ultimate load carrying capacity of the given pile. Now this ultimate load carrying capacity, this is having two components. So the first one is the point load carrying capacity, so the point load bearing capacity, and the second component is the ultimate skin friction resistance. Okay, now this ultimate skin friction resistance QS, it will be having three components because it's a 3-layered soil deposit. So QS1 plus QH2 plus QS3. Now these values QS1, QH2, QPU, somehow we know. So we don't know the QS3 because for layer 3, none of this angle of internal friction or the earth pressure coefficient is mentioned in this problem. Okay, so our job will be calculation of this QPU, QS1, QS2 separately, and then subtracting the summation of these values from the QU to get the QS3 value. Okay, so QS3 will be QU minus QPU minus QS1 minus QS2. Okay, so we know QU, so only we have to calculate these entities individually. QPU, that is the ultimate point bearing resistance or capacity of the pile, then the ultimate skin friction resistance for layer 1 and layer 2. Okay, okay, so this is a schematic for the given problem. So first of all, this is layer 1, which is having a thickness of 6 meter. Then this is underlain by layer 2, and subsequently they are 3. And these are the properties mentioned for the present problem. Okay, so now first we will try to establish the profile of the effective overburden pressure. Okay, because it's very essential to calculate both the ultimate point bearing resistance and the skin friction resistance. Okay, so and of course this for this problem we need not to consider the critical length. So therefore this effective overburden, so we'll calculate as per the conventional manner. Okay, so we'll not restrict the overburden pressure up to critical length and then it will become constant. So that concept we will not implement here. Okay, so first of all, for the first layer, so it will basically vary, the effective overburden will vary from a value of 0 to what, 15 times 6, that is 90 50. Okay, now for layer 2 it will vary from 90 to, okay, again the gradient will not remain same because the soil properties are changing. So this value, this is basically 90. Okay, so let me in this fashion, 15 times 6 plus 18 times what is the thickness, so the thickness is 10 minus 6, therefore 4. Now this value would be 90 plus 18 into 4, so therefore 162. And finally this 15 times 6, 18 times 4, and this 20 times 15 minus 10, that is 5. So 162 plus 100 is 262 50. Okay, so this is the profile for effective overburden along the length of the pile. Okay, considering all the layers, layer 1, layer 2 and layer 3. Now what would be the ultimate point resistance, point bearing resistance for the given pile as per Tomlinson's method? So QPU, this will be sigma V bar, sigma V prime NQ. Now what is sigma V prime? The sigma V prime is nothing but the effective overburden pressure at the pile tip level. So that means 262. And what is NQ? So NQ given to this problem as 130. Okay, so this is the bearing capacity factor. Now if you multiply, so okay, sorry, so this is small QPU.
Excuse me, sir.
Unit load bearing resistance.
Can you repeat this line once again?
Which one? This
QPU.
so QPU, this is the product of effective overburden pressure at the pile tip level, which we have calculated as 260 kPa multiplied by the bearing capacity factor, which is given to this problem as 130. Okay, so this value. So if you basically multiply this NQ with the sigma V prime, will first get the unit point bearing resistance, and if you multiply this unit point bearing resistance with the cross sectional area at the pile tip, then we will be having the ultimate point bearing resistance. Okay, so ultimate point bearing resistance QPU, so this is basically unit point bearing resistance multiplied by the cross sectional area at the pile base, so AB. Now what is AB? So this AB is simply pi by 4 d square. since this is a pile shaft of diameter d. Okay, and QPU you can calculate from this expression, 262 multiplied by 130. So 262 multiplied by 130, this much kilonewton per meter square. So obviously this ultimate point bearing resistance would be 262 multiplied by 130 multiplied by pi by 4 into 0.3 square. So the diameter of the pile is given as 0.3 meter. So I am getting the value for ultimate point bearing resistance as 2407.56 kilonewton. Okay, so this much value I am getting for the ultimate point bearing resistance. Have you got the same value?
Yes, sir.
Okay. Okay, now coming to the skin friction component, so QS. So as I mentioned earlier, so you will be having three components for QS: QS1, QS2, and QS3. Now, how to calculate this QS? So QS you can calculate. This is the product of unit skin friction resistance multiplied by the surface area of the pile. Now this unit skin friction resistance, this is again you can calculate from K sigma average prime tan delta. This K is the earth pressure coefficient, sigma average prime is the average of the effective overburden pressure, delta is the angle of wall friction, and AS, this is the pi dl. Okay, so surface area of the pipe. Now for QS1, so this will be, so this is for the first layer. So for the first layer, this K value, this is given as 1. Okay, so 1 times sigma average. Now what is the sigma prime average? So this is the average value I am writing here. So for the layer 1, so this is 0 plus 90 by 2, that means 45 kPa. Okay, so this is sigma prime average. Now for the second layer, so this is 90 plus 160 by 2. 90 plus 160 by 2, that means 126 kPa. And for the third layer, so this would be 162 plus 162, 262 by 2, that means 162 plus 62 by 2, this is 212 kPa. Though there is no need to calculate these values for the third layer. Okay, why? We'll see. Okay, so 1 multiplied by sigma average, this is 45. Then tan, what is delta? So delta, for the delta is basically 0.75 times the pi, friction angle of the soil. Now for first layer, the friction angle of the soil is 30 degree. So that means, so this value would be 0.75 times 30 into pi dl. Pi diameter is 0.3, again this is small d. Okay, as shown in this figure. And what is about the length of this layer 1? So this is 6 minus 0, that is 6 meter. So please calculate and let me know the contribution from layer 1 to the ultimate skin friction resistance.
105.4.
Yeah, very good. So 105.4 kilonewton. Now similarly for the second layer, you can easily calculate the contribution to the ultimate skin friction. So it will be 1.5, because here the earth pressure coefficient is different from layer 1. Okay, so it will be 1.5 times. Now what is the average? The average is 126. So 126 into tan of delta means 0.75 times phi. Here phi value is 35 degree. So 35 into 5 times 0.3 times. Now what is the length in layer 2? The length is 10 minus 6, that is 4 meter. So please calculate and let me know the contribution from layer 2 to the ultimate skin friction resistance of the pipe.
Three hundred 51.37.
Yeah, very good. 351.37 kilonewton. Okay, so now I think we can easily calculate the contribution coming from the third
Sir.
layer. Okay, so QU we know, QPU we know, QS1 we know, and QS2 we know. So from this equation, QS3, this would be QU, this is the ultimate resistance, minus the point bearing resistance, minus the skin friction resistance contributed by layer 1 and layer 2. Now QU, so this is 3450. Okay, so this is given to this problem, or rather the safe load bearing capacity is given. So when we multiply the safe load carrying capacity with the factor of safety, we got the ultimate load carrying capacity. Okay, now we calculated the point bearing resistance as 2407.56. So 2407 minus 105.4 minus 351.37. So how much is it? Can you please let me know?
It's a 585.67.
585.67. Okay, so this is the contribution from the layer 3 to the towards the ultimate skin friction resistance. So this much kilonewton. Now is this the answer? What do you think? Okay, so this may be the answer if you report the skin friction resistance as a whole. Okay, ultimate skin friction resistance. Now if you try to figure out, or if you try to evaluate the unit skin friction resistance, then you have to divide this value by the corresponding surface area. So that means A phase 3. So to calculate the A phase 3 value, so we have to divide this 585.67 by the respective area. So pi multiplied by 0.3. What is the length? So 15 minus 10, that means 5 meter. Okay, so finally you will be having this unit skin friction resistance as 124.8 kPa for layer 3. Okay, so this is for layer. So in terms of ultimate friction resistance, so this is 585.67, and unit skin friction resistance, this is 124.28.
Repeats once again, sir. FS3.
FS3. Okay.
Why we have to find this one? No, sir.
Okay, are you done?
No, sir. I'm telling that repeats once again.
Which one?
FS3.
Okay.
FS3.
So FS3. Now, how we have calculated this individual contribution for the ultimate skin friction? So we have calculated this QS. Suppose QSI, the unit resistance, unit skin friction contribution multiplied by the respective surface area. Now here we have got the ultimate one for layer 3 by subtracting QPU, QS1, QS2 from QU. Now to get the unit one, that means this FS3, here this I subscript is 3. So just you have to divide this QS3 by the respective area AS3. So QS3 is here 585.67, and AS3, this is nothing but pi times D times L. D is the diameter of the pile 0.3, and L for that layer 3 is 15 minus 10, that is 5 meter. Is it fine?
Okay, sir.
Okay. Okay. So now we'll take this third problem. So a 0.5 meter by 0.5 meter square concrete pile is to be driven in a homogeneous clay soil having undrained shear strength 50 kPa, unit weight 18 kilonewton per meter cube. The design capacity of the pile is 500 kilonewton. The adhesion factor alpha is given as 0.75. Now what we have to determine? We have to determine the length of the pile required for the above design load with a factor of safety of 2. Okay, so in this problem, factor of safety is specifically mentioned as 2. Now, unlike the previous two problems, so in the previous two problems we have dealt with mostly cohesionless deposit or granular deposit. Now in this problem we have to deal with clay soil deposit. Okay, so therefore the formula for calculating this ultimate load carrying capacity of a pile in clay will be different, na? So it will not remain same as we used for the case of, or in the case of, granular soil deposit. So here this ultimate pile resistance or load carrying capacity, so you can calculate from this formula. So this is CUB NC AB plus alpha CU into AS. Okay, so by utilizing this expression you can calculate the ultimate load carrying capacity of a pile which is constructed or which is in clay. Now what is CUB? So CUB, this is the cohesion at the base level of the pile. Okay, so at this level. What is NC? NC is the bearing capacity factor contributed by cohesion, and as you know, for a deep foundation this value should be 9 as per Skempton's theory. What is AB? AB, this is the cross sectional area at the base. So again this will be pi by 4 d square, and D for this present problem is 0.5 meter. Alpha, what is alpha? Alpha is the addition factor, and this is given as 0.75. What is CU? CU, this is the average cohesion over the length of the pile. Now as you can see, this is a single layer deposit or a homogeneous stratum. So this is a homogeneous clay stratum, so therefore this CU will be simply 50 kPa. And what is AS? AS, this is the surface area of the pile. Okay, now we'll start calculating this ultimate resistance. So this CUB, so this is the cohesion at the pile tip, so this is again 50 kPa. So 50 times NC is 9 times pi by 4 into D square. So D square is 0.5 square. Okay, so this is the tip resistance, and coming to the skin friction resistance, this is alpha, that is 0.75 times U, so 50, and AS. So AS is pi DL, so D is 0.5, but L, the value for L we don't know, and that is the objective of this problem that we have to determine. Now this QU we know somehow. How we know? So similar to the previous problem. So earlier in problem 2, the safe load carrying capacity was given. Here design capacity of the pile is given, and the factor of safety also given. Now if you multiply this design capacity with the factor of safety, you will get the ultimate capacity. So this ultimate capacity would be this design multiplied by factor of safety. Okay, now what is the value you are getting for this first component? 50 times n times pi by 4, 0.5 square. How much value you are getting? This is 450 into 0.5 square into pi divided by 4. So I think it would be 88.36 plus 0.75 into 50 into pi into 0.5, that means 58.9 L. Okay, so 58.9 L. So this is, if you basically simplify this equation further, so Q design is given as 500 into, oh sorry, it will be in the reverse way. So 500 into 2 minus 88.36. L will be 1000 minus 88.36. So did I any mistake in this problem? Yeah, so I did a mistake. So can you please identify this mistake?
How you get 500 into
500 into? No, I think this is fine. I did the mistake somewhere else. And that's a very big mistake. So I basically did the mistake in this part. So the cross-sectional area of the pile is no more circular. So in the previous two problems, we considered pile of circular cross-sectional area. However, for the present problem, this is a square concrete pile. So the cross-section, something like this. So 0.5 meter by 0.5 meter. So this is the value for B. Now for a square cross section, what is the cross sectional area? So this is B square. So that means 0.5 times square, 0.5 square. And what is the surface area? So this is 4BL. So 4 times 0.5 L. Are you getting my point? So earlier I did the mistake because I used the cross sectional area and the surface area of pile having circular cross section, uniform circular cross section. However, this is not the case for the present problem. So for the present problem, it's clearly mentioned that this is a square concrete pile with dimension 0.5 meter by 0.5 meter. Therefore, cross sectional area will be B square, 0.5 square, and the surface area would be 4BL. So 4B, this is the perimeter multiplied by L, length. So that will give you the surface area of the square concrete pile. Okay. So accordingly, these values will change. So please correct me if I am wrong at any moment. Okay. So 15 to 9 into 0.5 square. So this will be 112.5 plus 0.75 into 15 to 4 into 0.5, that is 75L. This is 75L. This is 102.5. So 1000 minus 102.5. So this is 887.5 divided by 75. So this will be 11.83. So the required length, this required length is basically 11.83. So this much length you have to provide to have a design capacity of the pile as 500 kilonewton and with a factor of safety of 2. And obviously the cross section of the pile would be a square cross section having 0.5 meter by 0.5 meter dimension. Is it okay for all of you? If so, then I can.
Yes.
Okay. Now coming to problem 4. So this is application of an underdimped pile. So a 25 meter deep board pile has a shaft of 1 meter diameter and enlarged base of 2.5 meter diameter in the lower 1.5 meter depth. So as you can see from this figure, so this is a pile which is having a single bulb. So that means this is an example of underdimped pile. Okay. So first of all, the uniform shaft diameter is 1 meter and the diameter of the enlarged base in the lower 1.5 meter portion is 2 meter. Now the undrained cohesion of the soil varies from 100 kPa at the top to 150 kPa at the base. So again, this is the difference with the previous problem, that is problem 3. So in the previous problem, we have considered that is uniform undrained cohesion throughout the pile length. However, here the cohesion, undrained cohesion is varying in between 100 kPa to 150 kPa at the pile top to the pile tip. Determine the safe load with a factor of safety of 2.5 and we have to take the adhesion factor as 0.45. So how to calculate this safe load for an underdimped pile? The same equation you have to use, that is CUB NCAB plus alpha CUAS, but with some little modification. Now what are those changes? Can you please tell me? To calculate the safe load carrying capacity of an underdimped pile, what will be the changes to be incorporated in this equation? Okay, so two changes or two important considerations you have to follow while you will use this equation for calculating the ultimate load carrying or safe load carrying capacity of an underdamped pile in clay. First of all, this, okay, so let me write down the formula first. So QU, so this is QB NC AB plus alpha Cu prime AS or Cu AS. Okay, so I am not changing the equation here. Now CUB, so this is the cohesion, undrained cohesion at the base of the pile. NC, this is the bearing capacity factor contributed by cohesion of the soil. 9, this is the base area of the footing, base of area of the pile. Now what is the base area of the pile for this problem? What should be the base area of the pile? Okay, so for this specific problem, since you are dealing with an underdamped pile with a bulb at the lower 1.5 meter portion depth, so this area of the bulb, cross sectional area of the bulb, you have to consider to calculate the base area of the pile, because the resistance, as you can see, so this bulb will be effective to provide the point bearing resistance. Okay, so this projecting bulb, that will give you the point bearing resistance. So you have to consider the base area of the pile accordingly. So instead of this simple pi by 4 times small diameter square, a small d square, which is the cross sectional area of the shaft, you have to use the cross sectional area of the bulb. So this is one change in this equation as compared to the previous problem. Now what is the second change? Now the second change is in this area, surface area. How? So earlier in this we have basically considered the entire length, that is this entire length for the calculation of skin friction resistance. So the entire length will be effective. However, for this problem, this projecting part, the length of the bulb, will not consider to be on the conservative side. Okay, so though you can consider, but will not consider. And further, a small distance of length twice d will not consider. Why? Because when due to the application of load at the top of the pile, when this pile will settle, there will be a formation of gap between the adjacent soil and the top of the bulb. So that's why this 2 times d we have to neglect to calculate the effective length of the pile. So therefore, these are the two changes which we should take care in the calculation of pile load capacity of a underdamped pile with single bulb. And again, this bulb is basically located at the lower portion, at the base of the, means close to base of the pile. Okay, so if this is not the case, if the bulb is basically located slightly, not slightly, as a very high, means considerable height from the base, this equation will not remain same. Okay, so that you please take care. So therefore this okay, now another concern is about the cohesion values. Now for the base of the pile, so cohesion we can take it as 150 kPa. Now what is about the cohesion in the second component, that is the skin friction resistance component, Cu? So since this cohesion is varying, so again you have to take the average of that. So this Cu will be, so you can use a prime symbol here, so Cu prime, this will be the average of this value 100 at the top and this value corresponding to this level. Okay, so this value we don't know, we have to calculate this value considering a linear interpolation between this level and this level, top level and tip level. Okay, now this equation will modify as per the given application. So CUB NC pi by 4 capital D square, not small d square, plus alpha cu prime pi d L effective. Okay, not the overall length. Now what is L effective? So L effective we can calculate here. So L effective, so this is the total length, that is 25 meter, minus, we are basically neglecting this length of the bulb, that is 1.5, minus 2 times D, that is 2 meter. D is there, basically 1. So 25 minus 3.5, therefore 21.5. Okay. Okay. Now coming to the this undrained cohesion, variation of the undrained cohesion, or the value of undrained cohesion at this level.
D left, once again. Sorry, L left.
L effective. Okay, so this is the L effective. This portion. This is the total length minus the length of the bulb minus this portion, and this portion we are basically neglecting only because of the formation of gap when the pile settles due to the application of external load. Okay, are you getting my point?
Yes, and yes, sir. And this point, how you get this point as a 2?
Which one?
2D power 2D.
This 2. Oh, this 2D.
Yeah.
This is from the literature. We are taking the reference of literature. So from the literature, it's observed that this length, there will be a small gap. So for this portion, there the soil will not be in touch of this pile. So if the soil is not in touch with the pile surface, then this pile will not having any skin friction resistance over this layer. Okay, so this reference, this 2D value, we are basically taking with the reference of literature. So this value you can get from the lecture contents or the lecture materials. So if you follow the lecture videos very sincerely, or if you go through the lecture contents which are uploaded in the on the course portal, so you can have the idea for this 2D, why this 2D is basically subtracted from the total length. Okay, now we have the L effective. I hope we have all the values which are required for each of these parameters, with the exception of this undrained cohesion value at this level. Okay, so now how to calculate this undrained cohesion at this level? So we'll go for some linear interpolation. Okay, so at 0, the undrained cohesion value is 100 kPa. At 25 meter, the undrained cohesion value is 150 kPa, and in between this is linearly varying. So therefore 21.5 meter we can easily calculate. So this Cu prime, so this will be 100 plus 150 minus 100 divided by 25 minus 0, 21.5. So this is the formula for interpolation. Okay, so now if you calculate this value, so 150 minus 50, 100, that is 50, divided by 25, that is 2, multiplied by 21.5, that is 43. So this value would be 100. I hope this value would be 143. Okay. So 143 kilometer per meter square. Okay, Is it okay? So how we are getting this?
No, sir.
Why not?
I think your value.
Why not?
Your value is wrong.
Huh?
I think your calculation is wrong.
For me or for you? This calculation part.
For you.
Okay. So okay. So this is what is the gradient of this line? So can you please let me know what is the gradient? What is the slope of this line? So this is linearly varying. Now what is the slope of this linear line? This is y equals to mx plus c. Suppose the equation of this line is y equals to mx plus c. So we are taking the reference x here. Okay. So this is x and this is y. Now this x is 0 here and x is 21.5 meter here. This 21.5 meter already we have calculated. There should not be any confusion. Okay. Now for y, this is 100 kPa here, and the value of y we have to calculate here. Now for that, this m we should know, because c we know. C is nothing but this 100 kPa. Now what is the value of m? Now the value of m, that will be 150 minus 100 divided by the distance. So this much increment you are having over a length of 25 meter. So what is the increment? The increment is 50 kPa. 150 minus 100. That is the increment. Over how much length? Over a length of 25 meter. Therefore, what is the gradient? So the gradient is 50 by 25. That I have mentioned here or written here. So 150 minus 100. This is the increment.
Yes, sir. It's okay, sir. It's okay, sir.
Okay. So therefore, I hope you have got this value. So 143 kPa. Okay. Okay. So this value is your 143. Now for the calculation of Cu prime, so we have to take the average of these two, 100 and 153, 143. Okay. So this Qu, so this will be CUV in the sense 150, NC is your 9 pi by 4 into 2.5 square plus alpha, the addition factor is 0.45 into 100 plus 143 by 2, this is the Cu prime, pi into 1 into L effective, that is 21. So please calculate. So this value would be 10319.78 kilometer. Q save, therefore we can calculate 10319.78 divided by 2.5. This is the factor of safety. So 4127.91 kilometer. Is it okay? The safe load carrying capacity of the given under file, we have got the value as 4127.19.
Wait, sir. Yes, sir. Done, sir.
Okay. Okay. So I think we can take the next problem. So the next problem is taken from GATE examination 2023. So a circular pile of diameter 0.6 meter and length 8 meter was constructed in a cohesive soil stratum having the following properties: bulk unit weight 19 kilonewton per meter cube, angle of internal friction 0 degree, and cohesion 25 kPa. So the allowable load the pile can carry with a factor of safety of 3 is this much kilonewton, and that you have to report by or after rounding up to 1 decimal place. So you have to adopt the addition factor as 1 and the bearing capacity factor NC as 9. So it's a very straightforward problem. So please, I'll request you please calculate this allowable load the pile can carry with a factor of safety of 3. Because just now we have solved a similar problem in problem 3. So first you need to calculate the ultimate load, then you need to divide this ultimate load by the given factor of safety, that is 3 here, and you can easily get the allowable load. Now what is the expression for ultimate load? What is the expression for calculating ultimate load of a circular pile in clay? So QU, this is CUV, same formula, NC AB plus alpha CU S. Now you know all the entities which are involved in this equation, so you can easily get the QU. Now if you divide this QU by a factor of safety of 3, you can calculate the Q allowable for the given pile. Okay, so please calculate and let me know what should be the Q allowable for the given circular pile of diameter 0.6 meter and length 8 meter. So here I am summarizing the data. CUV 20 kPa, cohesion at the base. NC, this is 9. IB, AB pi by 4, 0.6 square, 6 much meter square. Alpha 1, CU again 20 kPa, and AS is pi multiplied by 0.6 multiplied by 8. Just you have to substitute these values in the equation, in this equation. Have you calculated? So I am getting this ultimate load for the given circular pile as 440.61 kilometer. Now we have to determine the allowable load. So we have to divide this QU by the factor of safety. So 440.61 divided by 3. So 146.87 kilometer. This is the fine. So we have calculated the allowable load of the given circular pile of diameter 0.6 meter and length 8 meter as 146.87 kilonewton with a factor of safety of 3. So is it okay? May I move further? I am not getting any response from your end. So okay. So I am assuming that there is okay. Thank you. So we'll take our next problem, and this is the last problem for today's session. So one more problem is there, that is all about the homework. So we'll first solve this problem and then we'll discuss a little bit about the homework problem. Okay. So problem 6 is mentioned like that: a 300 mm diameter pile of 12 meter length was subjected to a pile load test and the following results are obtained. So in the first column the loads are given, and the second column corresponding settlements are, the recorded settlements are given. Now you have to determine the allowable load as per this IS 2911 part 4 1975. Okay. So this is also a very straightforward and easygoing problem. No such complications are there. So just you have to follow the recommendations which are given or prescribed by this Indian standard, that is IS 2911 part 4 1979. So can you please recall what are the recommendations prescribed by Indian standard 2911 to determine the allowable load for a single pile? So recommendations for allowable load will vary from single pile to group of piles. Okay. So please remember, right now we are dealing with single pile. So accordingly, we have to follow the recommendations for determining the allowable load. So what are those recommendations? So as I can remember, so we have to basically consider two conditions. So these conditions are shown here in this slide. So this is taken from the lecture materials. Okay. So the allowable load on a single pile shall be lesser of the following. So first of all, 2/3 of the final load at which the total settlement attains a value of 12 mm. So this is the first condition. 2/3 of the final load at which total settlement attains a value of 12 mm. So in addition to that, if nothing is specified, then the permissible settlement 12 mm is equal to 12 mm. If any other permissible value is specified, then load shall correspond to actual permissible total settlement. Okay. So if nothing is mentioned, then you have to consider the permissible settlement as 12 mm. So this problem, so this permissible settlement value is not specified, so therefore we will take the permissible settlement as 12 mm, and this corresponding to 12 mm settlement will try to calculate the final load, and 2/3 of that final load will figure out. So this is the condition 1. Now coming to condition 2, so this is 50% of final load at which the total settlement equals to 10% of the pile diameter in case of uniform diameter piles, and 7.5% of bulb diameter in case of underrimmed piles. So for the present scenario, this is a uniform diameter pile having 300 mm diameter. So therefore, so this first portion of the statement will be applicable. That means the settlement which is having a value of 7.5% of the bulb diameter, bulb in the sense the shaft diameter, that we have to first calculate, and then the final load corresponding to this settlement value we have to calculate, and then we have to take the 50% or half of this final load as the allowable load. Now we are getting two allowable loads. Okay, so corresponding to first condition and second conditions respectively. Now minimum of these two allowable loads will give you the final allowable load for a single pile. Okay, so I have a power cut here, so that's why I am switching off my video. Okay, so I think it's fine for determining the allowable load of the given pile based on the load settlement data, okay, obtained from the pile load test. Now here I have plotted the load versus settlement data given to this problem. So this is the curve which I have obtained. Now first we have to calculate the load corresponding to 12 mm settlement. Now this is the 12 mm settlement. Okay, so this interval is basically 2. So corresponding to 12 mm settlement, the load is this. So this is the load corresponding to 12 mm settlement. So that means 500, then 700. Sorry, this division is also, I think, 500 divided by 5, that is 100. So this is 700. Okay, so the first, from the first condition, this Q allowable, we are getting 2/3 of this load. So this load is 700. I think slightly more than 700, so 750. Okay, now this is 750, therefore 750 multiplied by 2/3, that means 250 multiplied by 2, that is 500 kilonewton. So this much load we are getting from condition 1. Now from condition 2, first we have to calculate the 10% of the bulb diameter, 10% of the pile diameter in case of uniform diameter of piles. Okay, I think earlier I mentioned wrongly, so it will be 10% of the pile diameter in case of uniform diameter of the pile. So 10% of the diameter 300, so that will give you 30 mm settlement. Now final load corresponding to this 30 mm settlement, again we have to calculate, or we have to figure out from the given pile settlement data, load settlement data. Okay, so this will be, I hope, as you can see, 1700. So this is 1500, this is 2000, so this is 1700. So Q allowable, this will be 50% or half of this 1700. So that means 850 kilonewtons. Now the final Q allowable, this will be minimum of these two, minimum of this 1 and 2 condition. So that means 500 kilonewton. Okay, so this will be something here. So in this way you can calculate the allowable load of a single pile based on load supplement data obtained from pile load test. So two conditions you need to follow: 2/3 of the final load at which total supplement attains a value of 12 mm if no other permissible or actual permissible supplement value is specified, and the second condition is that 50% of the final load at which the total supplement equals 10% of the pile diameter. This is for the case of, or in the case of, uniform diameter piles, and 7.5% of bulb diameter in the case of under-end piles. Now for the present problem, this is a pile with uniform diameter, so therefore 10% of the uniform pile diameter you have to consider. So this is 30 mm supplement. So this 30 mm allowable load is half of the 1700, so that means 850 kilonewton. This is condition 2, and from condition 1, 2/3 of the load which corresponds to a supplement of 12 mm, so that is 750. So 750 multiplied by 2/3, that is 500 kilonewton, and minimum of these two or lesser of these two will give you the final allowable load, that is 500 kilonewton. So this is the answer. Okay, so I think I cannot continue further. Okay, so I am having a power cut here, so I'll just read this homework problem statement of this homework problem, and I will leave this problem up to you. So you please solve this problem at your home and let me know about any difficulties which you face in solving this problem. Okay, so this problem is about a 16-meter long concrete pile which is driven into a layered soil stratum in such a way that the pile is 1 meter above the ground level. So whole pile length is not under soil, so 1 meter is above the ground level. The subsoil profile and the respective properties are given in the table below. The water table is at a great depth from the ground level. If the diameter of the pile is 0.3 meter, determine the safe load carrying capacity of the pile. Okay, so this is again an example of determination of load carrying capacity of pile in a layered soil deposit. However, in this layered soil deposit, we'll be having both type of soils. So purely granular and purely cohesive soil. Okay, so for the first layer, that is extending from 0 to 6 minus 6 meter, we are having a soft clay with 15 kilonewton per meter cube unit weight, this unconfined composite strength 40 kPa, and the adhesion factor 1. Now for second layer, which is extending from minus 6 to minus 10 meter, we are having dense sand, unit weight 17 kilonewton per meter cube, angle of internal friction 35 degree, and earth pressure coefficient
Sir,
2. Yeah.
let me show the graph at once.
Okay. So this is the graph. Okay. Okay, so coming back to this homework problem, now for the third layer, that is extending from -10 to -15 meter, we are having steep clay, unit weight 19 kilonewton per meter cube, unconfined composite strength 120 kPa, and the adhesion factor is 0.4. So with this given data, we have to report that the safe load carrying capacity of the pile. So due to this power cut, I am not able to proceed this session further, continue this session further. So I am ending here. So I'll request to all of you that you please solve this problem at your home. And if you have any doubts or if you face any difficulties in solving this problem, please let me know in the upcoming session. So we'll again meet on coming Sunday, that is on 17th of September at 5 p.m. and we will start that session with this problem. Okay.
Okay, sir.
Okay. Thank you for joining this session. So I am ending this session here.